Great. So yep, I'll be talking about making Formulog fast using unconventional data log evaluation. This is joint work with Michael Greenberg and Steve Chong. So before I get into our contributions, I'll give just 2 slides of background. If this works. That's okay. Okay. So what is data log? Well, we've seen it a couple times already today, but the way I'm going to present it is as a way to mechanize inference rules. So here we have inference rules, 2 of them that compute reachability from the node, from the root of a tree. Data log allows us to stick these inside a data log engine, provide a database of input facts, and the data log engine will produce for us output facts, like which nodes are reachable in the tree. How does it do this? It's going to use a bottom-up fixed point computation. A lot of data log engines are highly optimized, so this can scale to making tens or hundreds of millions of logical inferences. One of the big applications for data log over the last decade or so has been program analysis, because it's been found that analyses like points-to analysis can be encoded both very naturally and effectively in data log. A couple years ago, my collaborators and I took this a step further by developing Formulog, which combines data log and SMT solving. It also has some functional programming, but I'm not going to talk about that today. The motivation of Formulog was to extend the benefits of data log to SMT-based analyses like refinement type checking or symbolic execution that you can't encode naturally in traditional data log. So Formulog allows you to mechanize inference rules like this one, where you have SMT formulas occurring as terms within the rules, and then you also have SMT queries, such as checking for satisfiability. And what happens is when you evaluate this Formulog program, and you get to the satisfiability query, it's going to be sent off to a pool of external SMT solvers. And the key thing is that for a Formulog analysis, the SMT solving component can be one of the largest parts of the computational workload, unlike a traditional data log analysis. And that leads to really the question at the heart of this talk, which is if we have one of these Formulog-based analyses that uses a lot of SMT solving, we want to make it faster. How do we do that? Are the traditional techniques for high-performance data log sufficient? Or do we need something novel that better accounts for that SMT workload? And we'll explore both approaches in this paper. So we make the following contributions. We developed a compiler from Formulog to Soufflé, which, as it's been mentioned, is this existing, well-known data log system. We've developed a novel data log evaluation algorithm called eager evaluation. We've implemented eager evaluation in both Formulog and Soufflé. And then combining our compiler with this new data log evaluation algorithm, we've achieved speedups over published analyses written in more traditional languages. So I'll talk about all these contributions, but I'm going to start with the final one. So with the techniques we developed in this paper, Formulog is a competitive analysis platform. What do I mean by that? So we've been able to encode a range of sophisticated SMT-based analyses in Formulog. We've been able to run them on substantial workloads in terms of the number of logical inferences or the number of SMT calls, or both. And we've achieved good results. So on 20 out of 23 benchmarks, the Formulog version has actually beaten the version written, like the handwritten version in F#, Java, or C++. So I hope this makes you excited to learn more about how we're able to achieve these results, because that's what we'll be talking about. So the first thing we did is we developed this compiler from Formulog to Soufflé. So Soufflé is a high-performance data log system, and by compiling to Soufflé, we're able to take advantage of the traditional techniques for making data log fast. Like Soufflé really embodies those techniques. How well does that work for Formulog? Well, it gives us some speedups over our baseline Formulog interpreter, but they're not evenly distributed across the case studies. So the case study where we don't use much SMT solving gets the biggest speedup, And the case studies where we use a lot of SMT solving don't get much speed up, which makes sense since those traditional techniques are really only optimizing that data log component of the workload. And that leads to the natural question, like how do we do better for these SMT-heavy analyses? Well, our hypothesis is that semi-naive evaluation, which is really the bedrock of high-performance data log systems, is actually not a good fit for these SMT-heavy workloads for two reasons. One, it batches work, and two, it performs essentially a breadth-first search of the logical inference space. And we can see that in our little reachability tree example. The way semi-naive evaluation works is in this sequence of rounds. So in the first round, it computes everything that's reachable in 0 steps from the root of the tree. In the next round, it computes everything that's reachable in 1 step. In the round after that, everything that's reachable in 2 steps. So here we have this very explicit round structure that builds in batching. And then also, we can see that we're doing not only a breadth-first search of the tree, but this also corresponds to a breadth-first search of the logical inference space in terms of proof height. So why is this a bad thing for these SMT-heavy analyses? Well, let's extend our example and imagine that now we're doing reachability in a program execution tree, so something like symbolic execution, where our tree, now the edges are going to be labeled with SMT formulas. And there are 4 work items here, each one corresponding to a different edge to traverse. And I've annotated each one with sort of the SMT formula that needs to be satisfiable for that edge to be traversable. So the idea is it's reachability, but it's modulo the satisfiability of the path condition leading up to a node, like you'd expect in symbolic execution. So the first issue is that breadth-first search is going to limit the amount of incremental SMT solving that can happen, because typically adjacent queries are not going to share conjuncts. So we can see that here's the work items in a breadth-first search order. We can compare this to what would happen if we did explore this tree using depth-first search. And we can see that there is sharing between adjacent queries. So some of those conjuncts are shared between the queries, which would give the SMT solvers more opportunities for incremental SMT solving and lead to faster SMT solving times overall. The second issue has to do with batching. And so if you have slow SMT calls, batching can exacerbate the way that those calls become bottlenecks. So here we have 2 threads, and we can see that thread 2 is waiting for a long time for thread 1 to complete if that green work item is like a long-running SMT call. If we don't batch them, everything is a lot more condensed, and the overall computation time is going to be shorter. So recognizing these limitations led us to develop this eager evaluation new data log algorithm. And whereas semi-naive is doing this batch breadth-first search, eager evaluation is going to do an unbatched depth-first search of the logical inference space. There's still some similarities. So both algorithms are parallelizable. They're both incrementalized in that they focus on novel inferences. So this is like the delta relations in semi-naive. And we'll see that there's enough overlap that eager evaluation is largely compatible with existing research and engineering on data log, which is a key to making this practical. So how does eager evaluation work? Well, in a nutshell, we can sort of split it into 2 parts. So you can imagine that you're partway through data log evaluation. You've made a bunch of inferences. One thing you need to do is choose which of these inferences to explore next. And the way that eager evaluation does this is through work stealing parallelism, which most of the time processes work using a last in, first out order. This in turn gives us something like an unbatched depth-first search of that logical inference space. In the second part, you've chosen that inference. Now you need to evaluate the inference rows on it to derive new inferences. Well, luckily for us, we can reuse the machinery from semi-naive evaluation. And this is really key because these techniques, so rule evaluation, is typically one of the most highly optimized parts of Datalog engines. And it's a key for the practicality of eager evaluation that we can use those. Eager evaluation is a work stealing-based algorithm where work item is a rule specialized on a novel inference. So here you've derived that node A is reachable. You can specialize the rule for reachability on that inference, getting out this specialized rule that says everything that's an outgoing neighbor of A is also reachable. In eager evaluation, each worker thread is essentially going to perform a local depth first search. So this is the logic for each worker thread. You can think of this as like the logic for thread I. And I'll break it down into a few parts. So first, the thread is going to find the next work item. And the first thing it does is it looks in its own work list and sees if there is one there. If so, it will take it. Otherwise, it will try to steal a work item from another thread. So that's where the work stealing comes in. And the second part is when the actual work happens. So this is where the rule, which is the work item, is evaluated. New facts are inferred, and those new facts are then used to create new work items, which in turn are pushed onto the work list for the current thread. So two things to note here. So the first is that most of the time, work items are processed in this last in, first out order, and this gives us the depth first search. And the second thing is that this rule evaluation here is going to reuse that semi-naive machinery, as I mentioned. So that's eager evaluation in practice, in principle. How does it work in practice? So we've implemented it in both Formulog's interpreter and the Soufflé code generator. And our results are positive, that it's both practical and effective for these SMT-heavy workloads. First, we were able to add it relatively easily to both Formulog and to Soufflé's code generator. So amazingly, it only took 800 lines of code, which was pretty surprising. And the second thing is that it achieves speedups over Soufflé's standard code generator for semi-naive. So this is true even in the case of our Formulog interpreter. So the Formulog interpreter is something like 5 times faster than the code generated by Soufflé if it's using semi-naive. And if we compile eager evaluation, we get some additional speedup. So taking a step back, what does this mean for sort of our original baselines? So when I was talking about the compiler, I was comparing against the semi-naive interpreter for Formulog. And I was bemoaning the fact that for the SMT-heavy analyses, compiling them with Soufflé doesn't actually give that much speed up. What does this look like if we add eager evaluation to the mix? Well, it turns out for SMT-light analyses, this does not help you, actually hurts you a little bit. But for these SMT-heavy ones, we get some substantial speedups, which really indicates that this evaluation algorithm we've developed, eager evaluation, is a good match for these SMT-heavy workloads. So in conclusion, we've seen this compiler from Formulog to Soufflé. We've seen this new Datalog evaluation algorithm, eager evaluation. We've seen it implemented in both Formulog and Soufflé. And we've seen it achieve speedups over published analyses written in languages like Java and C++. What are the takeaways from this? Well, the first is that takeaway is that Datalog in general, and perhaps Formulog in particular, can be a realistic platform for these SMT-based analyses, at least as far as performance is concerned. And the second is that new Datalog workloads might require new evaluation techniques. So as has been mentioned earlier today, like Datalog has come a long way from its early days as a database query language with all sorts of new applications. We might expect that as these applications continue to evolve, we'll also have to come up with new ways of evaluating Datalog that better match those workloads. But that's one of the great things of working in a declarative paradigm like Datalog is that we actually have this flexibility, so we can do this. With that, I would just encourage you to check out Formulog on GitHub. We have a new tutorial about how to use Formulog to implement a refinement type checker. And thank you.
Have any questions?
Hi, thanks for the talk. Given I have a Soufflé program, I want to use the eager evaluation. What are the steps I need to take?
Like there, you just add a flag.
And then I guess you have evaluated the eager evaluation on a larger range of existing Datalog programs that don't have this SMT-heavy load. So I'm curious to hear if the slowdown you observed in the one case, if that's generalizing to all the other ones or not?
So like in general, eager evaluation is not going to be a good fit for a lot of like traditional Datalog workloads. We've seen a couple cases where you have like doing reachability over trees where the trees have a particular structure with where like the finer grained parallelism of eager evaluation helps. But typically, like the advantage with semi-naive is you have this batching, which is going to cut down a lot of overhead that eager would otherwise introduce.
Okay.
Yeah.
Thanks.
Cool talk, thanks. So if I understood this algorithm, so a couple of questions, right?
Yeah.
If I understood this algorithm correctly, it's a work stealing algorithm, so the speed up is all because of multi-core evaluation. Follow up to that, something that keeps coming up every time I read about Datalog evaluation, people start talking about top-down, but the lesson of 30 years seems to be that top-down evaluation doesn't work in practice, that semi-naive is all that we have. What happens, I mean, you seem to be in the same paradigm of semi-naive, you are exhaustively computing the fixed point. What if you decide you're not going to invoke the SMT solver at all because you don't care about some rules? Could top-down evaluation actually be helpful for Formulog?
So the first question I think was about parallelism and like where the speed up is coming from. Well, so all the Formulog interpreter, the semi-naive version, and eager evaluation are both using the same form of parallelism internally. And then for Soufflé, the semi-naive evaluation there is using OpenMP for parallelism. And then we're using like TBB's library for eager evaluation. So they're all, like all these implementations are parallel, yeah.
Yeah, but what about top-down evaluation? What if you don't want the full fixed point anyway?
Yeah, so I guess the answer would be you could apply like magic set transformation, and then that would cut out derivations that you don't want to do. I haven't thought too much about implementing top-down for Formulog.
Okay. Thanks.